Okay, let's continue then talking about Chapter 10, where we left off the other day. We were discussing a number of types of defects that are typically found in software that your job is to detect when you're doing testing. And we were up to the point of talking about looking for null conditions. Null conditions are conditions where some value in the system is going to be 0, where it normally isn't. Okay, so an empty list, an input value of 0. These are typical situations where you might expect to get errors because the system will not go through any loops at all, and therefore some data, some values are not set. It might not get the 0. It might get some large number instead, or it might try taking the square root, or doing some other mathematical operation where 0 doesn't make sense. Okay. And so a lot of algorithmic bugs come around in null conditions, and a lot of the time people don't test for null conditions because they're unusual. You may expect there will always be, for example, employees in a department, right? And so the tester never thinks to test for a department with 0 employees, but occasionally it can happen for various reasons in the process of reorganization, or in a new department added, or everybody resigned all of a sudden for some strange reason and they haven't yet filled the staff positions. That kind of thing can happen. And so not testing for null conditions can cause interesting bugs and crashes. The only real testing strategy is to, well, first of all, if you apply equivalence class testing and you think of 0 as being a boundary of a valid equivalence class, then you'll get it that way. But in general, brainstorm. Get together with your other testers and think, what are the possible null conditions that we ought to test for? And go test for them. A similar situation to null conditions is with singleton conditions. Singleton conditions are conditions where you have one, not many. Okay? Or perhaps 1, not 0. Okay? Situations where you don't expect to only have one, you expect to have more than one, but you only have one. And again, you can have similar kinds of defects occurring in these situations. For example, if you try and take the standard deviation of a set of values and you only have one value, you'll get a mathematical error occurring, just like you would get a mathematical error occurring if you had 0 values. Okay? So 1 can also be one of these odd values, a little bit strange. And then you have the opposite, non-singleton conditions, the conditions where you have more than one value, more than one item in a list, a number higher than 1, where it almost always is 1. And so the tester forgets to test for that occasional case where there is more than 1. And again, you run into strange bugs. So again, the testing strategy is to brainstorm for these cases. Again, the purpose of all these points is to raise your awareness about strange things that ought to be tested for that sometimes people forget. Off-by-one errors are a classic kind of error. We talked about several ways which they could be reached earlier on, particularly not looping through a loop the correct number of times, 1 too many times, 1 too few times. There are many other circumstances where off-by-one errors occur. In ordinary programs, even today, I still occasionally see off-by-one errors in graphics. It's a very common situation where you notice there's a line of pixels missing, or things are just shifted just a little teeny-weeny bit because they did a calculation, so we're going to put it on the screen here, and they added their calculation resulted in adding 1 instead of 0, or basically calculations being off by 1. Now in graphics it's not always a bad idea, it doesn't make much difference quite often if the thing is shifted by 1 pixel, but it can make a big difference in certain kinds of situations, especially in situations where these off-by-one errors add up over time. So for example, if you accidentally gave every employee in your organization an extra $1, and you had 10,000 employees, and you did this every payday for several years, that would cost you a lot of money. Okay, so particularly common kind of defect, typically caused by, as I said, running loops 1 too many, or not getting a greater than instead of an equal condition, or something like that, in your logic. The basic strategy here is to be very careful to verify the numerical, the counting operations. What people often do when they're testing is they eyeball the results. They say, oh, that looks like the right result. Okay, it's got to be right. But what you really need to do is you need to do the calculation on a calculator or have a separate program calculate the calculation, which hopefully is not going to have the same bug in it, and double check to make sure all your calculations really are coming out to what your program says they are. Okay? So here is a typical example of an off-by-one. This is a classic bug in the C style of programming where you have starting points at 0, initializing I to 1. Anybody who knows anything about C and Java and C++ won't do this after the very first few programs because they get habituated to starting at 0. But it is quite common for people to initialize some value, some variable to 1, say, you know, the minimum number or starting point, and then to say I equals that starting variable and forget that in fact it was initiated to 1 instead of 0. And also you can have problems at the other end by using less than instead of less than or equal to, things like that. So one of the strategies to avoid this is to make sure that you don't do this style of iteration through loops. Okay? Don't use the for loop. Where possible, use iterators using has next. It's a much better style and it prevents off-by-one errors because the system takes care of all the counting for you. Question?
Can you repeat why we cannot use I equal 1 for the for loop?
Because in general, when you have arrays and collections in Java, the first index is 0, right? Okay, in the Java, C, and C++ programming languages, you index 0. So if there's 5 elements, it's 0, 1, 2, 3, 4. Operator precedence errors. These are classic situations again where you see multiplication being done first before addition, which is what you would expect, but maybe that wasn't what the algorithm called for. And so inappropriate use of parenthesization would be a classical kind of thing. And some of these bugs are very obscure and rarely show up. So for example, if, as in this slide, it says that you're doing a calculation, and again, all these calculations would come from the requirements, so you can check them in the requirements. The result of some calculation ought to be x times y plus z. Okay? And maybe it should have been x times brackets y plus z. The bug was that the parentheses were left out. Okay, well, that would show up in many circumstances by completely wrong calculations. But what if z was normally 0? If z was normally 0 almost all the time, this bug wouldn't show up until those occasional circumstances where z is not 0. Okay? So one of those obscure kinds of things that would just disappear normally and would show up very, very rarely, and people say, why the devil didn't we notice that before? Well, it's because sometimes one bug can hide another, okay? Or one rare circumstance can hide a bug. So you have to be very careful when you have requirements that give specific formulae to look to analyze the formulae mathematically and say, are there circumstances where this would give particular types of results and might give rise to particular kinds of bugs. And then we have the use of inappropriate standard algorithms. We've encouraged you to reuse code throughout this course. And so you're going to reuse standard algorithms for sorting and for searching. You almost never code a sort. You will have learned how to code a sort in a data structures course, but in actual fact, in practice, you'll be very rarely put in the position where you have to do that yourself. You reuse the code from somewhere else. The question then is that are you doing the correct reuse? Are you reusing a sort or a search that is appropriate for these circumstances? And if you don't, you can end up with bugs in your system that are unexpected. And the idea is that to be a good software engineer, you have to have a good understanding of the underlying mathematical theory behind algorithms, which most software engineers will take a course of. Computer engineers might lack some of that, because they have to do all the mathematics for hardware. But certainly for software engineers, you very much need to get into understanding issues to do with algorithm analysis. And that will lead you to understand when to use the right algorithm and when an algorithm is clearly wrong. There are a few circumstances we can look at. For example, inefficient sorting is a classic thing. Okay, everybody knows that there are certain very bad sorts that were one time taught. A bubble sort is the the classic bad example. In fact, when I was first taught how to sort, I was taught a bubble sort. Nowadays, anybody who teaches sorting first by teaching bubble sort should be shot. And clearly there are much better ways of doing sorting which are much more efficient, and programmers should realize that is the case. Inefficient searches are another similar classic category of things which you should avoid. So just doing a linear search unnecessarily when you have large volumes of data and it's sorted. Okay, so make sure that you test, and you can test for these things. You can test sorting to make sure the sorting is done efficiently by, say, sorting 1,000 items and then doubling it to 10,000. Okay, what you want to make sure is that you don't get 4 times the slowness. It doesn't slow down 4 times. You need to make sure that you've got an n log n sort algorithm, or you want to make sure that you've got a log n search in a large data set, okay, assuming the data is sorted. Okay, so these are the kind of things that you would know if you have an understanding of searching and sorting, which I think most computer and software engineers will have. But there's a lot more than that beyond just searching and sorting in algorithm analysis. Non-stable sorts, okay, are sorts which when you sort on one column, it will shuffle the values in other columns. So for example, if I've got data sorted by name, and then I sort by city, okay, I would expect that within the cities, the names would stay sorted. Okay, that's a stable sort. If I find that when I sort by city that the names get all jumbled up within the cities, then it's non-stable. And generally speaking, for presentation to users, that would be a bad idea. And so you want to make sure that you test for that kind of thing to make sure that, in fact, for end-user presentation, that sorting is stable, because otherwise users will get rather annoyed. And case sensitivity of searching and sorting is another issue, okay? There are many subtle, very, very subtle circumstances where bugs occur because people have either assumed case sensitivity or assumed it to be not case sensitive and designed searching and sorting algorithms that then don't work properly under those circumstances. And so again, you have to test with bodies of data when you're searching and sorting which have mixed case, if that's allowed in the data set, and you search for the uppercase, you search for the lowercase, and you get the result that will be expected by the requirements. Okay, even, it's interesting, just this weekend I was reading a bug list in a program I was installing, and they said known bug had problems with when you enter names which have the same character sequence but just differ by case, because they discovered a bug well after testing that was caused by that. And an interesting thing is different file systems behave differently. So for example, in the Macintosh, it behaves exactly like that. It preserves case, but if I create a file name which has the same letters, but they don't differ between, but they differ only in case, it will treat them as the same. And it will tell you you've already got that file name in the system. And that's intrinsically built into that particular style of file system. And there are other file systems that work the same way. Okay, so that gives rise to portability problems. You know, you port the thing and it says it's supposed to work the same. That's Unix, and so you port it from one Unix system to another. Well, they're not always the same, and that's one of the differences in that particular style of operating system. Okay, so little things, little subtle things, and there's hundreds and hundreds of these things that you learn as you get to know the ins and outs of different kinds of algorithms. Any questions? So we've talked about algorithms in general. There's also some things that you have to test for that are specific to numeric algorithms. Numeric algorithms are algorithms that are basically working with floating point data and are calculating results that have to have a certain precision. Okay, so typically in engineering applications beyond software engineering, so mechanical engineering, civil engineering, chemical engineering, scientific applications in biology, chemistry, physics. These are the typical circumstances where we have floating point data to worry about. We also have fixed point data, which is common in business, where some of these problems also occur. Fixed points data is data where you want to preserve a fixed number of points after the decimal point, typically 2 digits for cents, and you have to worry about that. So the first classic numerical defect to watch out for is not using enough bits or digits. Depending on how you're doing your calculation, it might be bitwise or it might be digit-wise. Typically in business applications, you're concerned with digits. Okay, but in scientific applications, the number of bits might be more applicable. And so what you have to do is you have to say to yourself, has this programmer designed the system so that it can capture the correct number, the amount of precision that we need? Okay, so if we need precision down up to 7 significant figures or 10 significant figures or a certain number of bits, will the system be able to deal with that amount of data? And so what you need to do is you need to do calculations that have that number of digits and significant digits and make sure that they're dealt with properly. If you're dealing with integers, a similar related problem occurs, and that is, is it storing numbers that are large enough? Okay, so for example, if I have a counter that's counting and counting and counting and counting, and eventually will roll up to the maximum value that can be stored in an integer, and then it will perhaps roll over to 0 or give you an exception depending on how the program is designed. So what you need to do is you need to exceed the limits of the number of bits or number of digits that have been set aside by making sure that you test with large values or values with lots of significant digits and make sure things are properly handled. And not using enough places after the decimal point is another issue. This can be an issue in currency calculations where you don't do enough, or stock value calculations where you end up rounding off inappropriately and ending up with dollar figures when you needed cents. You may say, well, we're only losing up to $1, or typically 50 cents on average, which won't necessarily be a problem in one calculation, but if those kind of errors add up over time, that can certainly be a big problem. And so you need to make sure that you have the capacity to store these things. This is similar to the previous one. In the previous one I was talking about not enough digits. In here I'm talking about, I guess this is the slide for not enough significant figures. But similar kinds of strategies involved in testing. I know that when I was, one of my first programming jobs, I was developing the system for a branch of the medical care regime, the Medicare system in New Brunswick for a particular kind of doctors. And basically it was a billing system, an early billing system for a particular medical specialty. And so I was working for the government, and we were going to be getting data coming in from these doctors, and one of the fields was the total amount of money that had been paid to a doctor in a year. Okay, and well, how much do doctors get paid? Well, in those days, which was 1985 time frame, it was reasonably safe to think that probably doctors would typically get 100,000, maybe more, but a million would be certainly safe. But hey, what the heck? We'll use 10 million. We've got to be safe. And this was a fixed size field in a database. Okay, so we had the maximum number of digits we could store would allow for 999,000 $9,999,999.99. Okay, so that was supposed to be the maximum salary. And no doctor's going to be paid more than 10 million, right? That's got to be safe. Well, there's two problems there. One is, what if there was a massive inflation in Canada? Well, we hope that won't happen. And if it's going to infect all computer systems if we do have those kinds of things. You don't want to be in the Italian lira system where where people were getting paid regularly $1 million a week. That would be a problem, but that's probably unlikely. The more insidious problem occurred when we actually put this system into production. And shortly thereafter, we ended up exceeding the capacity of this thing. And how on earth is some doctor really getting more than $10 million? The answer was no. But what happened is that in one particular hospital, they had a corporation set up that was a whole bunch of doctors that were billing as one, which apparently was perfectly legitimate, but nobody had put this in the requirements, and nobody had thought about it as a possibility. And so the group of doctors together had been paid more than $10 million in that year, and it exceeded the capacity, and we had to do an emergency fix. Okay. So just things you have to think about that are very subtle sometimes. Ordering operations poorly so errors build up. Okay, the notion here is that if you're not careful when you're doing certain kinds of mathematical operations, you end up gradually adding and adding and adding errors, so those errors become more visible. And I mentioned this notion of of losing a few cents in every calculation. Well, gradually those errors will build up. You can design your computations to minimize this kind of thing. The classic example of ordering operations poorly so errors build up occurs when subtracting. If I have floating point numbers and I subtract a very small number, let's say 1, from a very large floating point number, let's say 10 to the 20th, which could happen in physics, okay? Or let's even 10 to the 14th, okay? Some number that could be reasonable in certain kinds of calculations. Or I subtract 0.007 from 10 to the 9th, okay? Depending on the precision available in your floating point system, it may well be that subtraction results in no difference to the number you're subtracting from, okay? Take an arbitrary example, subtract 1 from 10 to the 40th. The answer is 10 to the 40th, because it can't store 10 to the 40th minus 1. It doesn't have enough precision to store that value, okay? Now, if you have a calculation that is repeatedly then subtracting small numbers from a large number, those small numbers won't be subtracted accurately. They might not be subtracted at all, or they might be only a small, limited amount of their precision might be subtracted from the large number. So over time, you're going to get errors building up. In the worst case, you expect to be subtracting gradually over time until you get down to 0, but the large number never budges. It sticks at that large value and never moves, because you think you're subtracting, but the result is equal to the original. And it goes on forever. Okay. And so what the strategy there is, instead of subtracting from the large number, the solution is to add the small numbers, and when you've finished adding all the small numbers, then you subtract the total from the large number. Okay? So that is a classic technique that is taught in any numerical computational course. Okay? And this is a typical kind of course that you might want to consider taking if you're doing scientific or engineering computations. They also teach about how to do calculus and things like that with numerical values. But that's the classical kind of error that you have to watch out for, and you have to test for that by testing large numbers and small numbers combined in any kind of scientific system, making sure that they work properly and that you don't get errors unexpectedly. There's an example of that in the book, okay, of that kind of style of problematic calculation. Another classical numeric defect is assumptions that floating point values are exactly equal to some other value. Okay, so the classic test is if something equals 3.14, okay? You know, testing to see if something's equal to pi. Well, you know, you don't do that, because how many digits does pi have? It has an infinite number of digits. And how many digits will your calculation result in? Certainly not that infinite number of digits. And so there's an arbitrary guess as to how many digits, you know, the value you have is as opposed to the value that you're comparing. Okay? Another situation is you have a floating point value and you want to stop calculations when it reaches 10. So you say, if x equals 10, then get out of the loop or something like that. Well, the point is that x might be 9.99999, never equals 10. Okay, that's a typical kind of thing that happens with floating point values. They don't actually exactly equal what you expect them to. And so the answer is when you're doing comparisons with floating point values, you always use less than or equal to, greater than or equal to. You never use an equal sign exactly, because you'll end up with situations where you don't get the floating point value exactly equal to what you expect it to be. It's off by some small epsilon. Okay? And so standard boundary testing should detect this type of defect, where you have your equivalence class and you say we're going to test at the bottom range and the top range and make sure that we test the value plus epsilon, the value minus epsilon, where epsilon is the smallest possible change in value that you could possibly enter into your system. Any questions? Okay, so here is a circumstance where I've demonstrated that. Here I'm doing a loop on doubles. I don't know why I would want to do this looping on doubles, but perhaps inside my calculation somewhere I'm using d, the value, in a floating point computation. And so I'm looping using floating point values to prevent the internal conversion. I don't think you should loop on floating point values. You should loop on integers. But if somebody did loop on a floating point, and then you end up with this d not equal to 10, and I'm incrementing by 2, this might work in some programming language. But you should never ever rely on this calculation working adequately and stopping at 10. Okay? Because even though a well-designed programming language will correctly add 2, 4, 6, 8, 10, hit the 10 and stop, some subtle variations in programming languages or operating systems, especially if written in the C language, which isn't quite as standard as Java, will not necessarily stop at 10. You'll have 9.99999 or 10.00001. Rounded off, you don't maybe not even see it when you display the result, but it is not exactly 10, and so it will then go on forever. So you should do something like this, or d less than or equal to 10. But you should certainly avoid comparisons to exact values. Okay, so that brings us to the end of the second general category of defects we need to test for. The next category is defects in timing and coordination. If you remember, I mentioned that one of the main categories of functional requirements is timing and coordination requirements. These are requirements for systems where things have to happen at precise times or in precise sequences, and therefore there are whole classes of defects where things go wrong. And there are a number of styles of defects that everybody should know about when you're dealing with any kind of system that involves any kind of concurrency and any kind of timing. The classic one is the deadlock. Deadlocks can occur in everyday life. So on the slide 30 here we have this picture of gridlock in traffic, okay, in a New York style system where you have cars heading in. First I'm showing it on 2 lanes, okay, so I've got here I've got a car driving in on the left and cutting across the traffic, but it's getting blocked by traffic coming the other way, and further down the line I've got other traffic cutting across going this way, and it's holding up these guys from moving out, and they're all holding each other up. The one that people are most familiar with is the four-way gridlock, where I have traffic coming on in each lane, blocking some other path of traffic, and so eventually nobody can go anywhere. Somebody has to back up. And this can really happen in really busy cities. And they try and design traffic light systems to prevent this from happening and so on, but it can really happen from time to time. Especially if you have construction or something. And here's an example of that. Imagine that we've got some bunch of construction workers get into a city and all of a sudden put up "can't go this way" signs because they're about to do construction down those streets. You've got some cars driving around these blocks, and each time they get to an intersection, then they realize, well, they can't go one way because it's a one-way street, and they can't go that way because it's construction here all of a sudden. And so they got to turn. In this case, they're turning right. Sorry, turning left. And they get to the next one, they got to turn left as well. And you know, eventually they realize there's no way out of this loop. They've got to keep going round and round and round and round and round. Now, this is actually not called deadlock. This is called livelock. So deadlock is the situation where all the traffic grinds to a dead halt and can't go anywhere. Livelock is where some traffic can keep moving, but it can't go where it wants to go. It just keeps getting stuck in a loop and can't actually move. So in the first case, the CPU is not executing. It's sitting in wait states, waiting for input typically. And in the livelock case, the CPU is churning away at high speed, and you think you're in an infinite loop, but you're not. You're not actually in an infinite loop in the classic sense of going around a while loop over and over again. You're in a livelock situation where there is some part of the computation that is running, waiting for some value, and the value never comes because all possible paths are being blocked. It has the same effect as being in an infinite loop. It appears that way to the user, but its livelock is slightly different. Okay, so you just imagine these streets as being threads that are waiting for each other, and that's the notion of deadlock or the notion of livelock. Okay? And so the question is, well, what do we do about this? How do we test for these situations? Okay? The classic types of deadlocks and livelocks occur with situations that are difficult to reproduce. So for example, I have one thread that is waiting to read a value from a database. Another thread has that database locked, and that second thread is waiting to read a value that the first thread has got locked. And these locks might occur only paired like that in very, very rare circumstances when perhaps two completely separate programs get together and run at the same time. And highly unusual, highly unexpected, but it can happen. Okay? And therefore it's very hard to anticipate these and hard to reproduce because the timing may have to be exquisitely precise. These things may happen, 1 in 10,000 cases by random chance. And so you try to reproduce it, you've got to be accurate to the millisecond maybe to get that deadlock occurring. And so in actual fact it turns out that testing is often not perhaps the best way to detect livelocks and deadlocks. The only thing you can do with testing is to verify certain kinds of properties, maybe in white box testing, you might be able to set some things up, but and you can try varying the time consumption of threads, slowing threads down to try and increase the time span in which these deadlock situations can arise, running large numbers of threads to increase the chance, or just doing very bulk testing, testing huge amounts of transactions over and over and over again, to see if eventually you'll stumble into one of these cases. But even when you do stumble into a case, you've got to detect it and understand what caused it at that point. So it's a bit tricky to test for these things. And inspection, which is the other style of quality assurance we'll talk about later, is often something you should consider. Let's take a look at a couple of cases in actual software. Okay, this is a UML diagram on slide 32 of actual threads executing. So we've got thread A and thread B, and they're accessing object O and object P. Okay? So what happens is that thread B comes along and locks object O. Thread A comes along and locks object P. And then thread B says, well, I want to modify object P. But unfortunately thread A has a lock on it, so I have to wait. And thread A at the same time says, well, I want to lock on object O. It might well be that both of these threads basically need to modify both of these variables together. In fact, they may even be exactly the same code executing in two different threads. Okay, nothing to stop that from happening. Same code operating in different threads, and they both need to modify O and P at the same time, but you get the lock on one, they get the lock on the other. And when he gets the lock on the first, the other one's got the lock on the other, and they end up waiting for each other. Okay? So here we have the classic deadlock situation, two-way deadlock, they're both waiting for each other. And what can you do about this? Well, you end up killing the program, killing one of the threads to get out of this. You can have various systems which might be prone to deadlocks, have algorithms running in the side that search for threads that are hung. If a thread's been waiting for more than a certain number of milliseconds or seconds, it'll take corrective action by killing one of the threads and restarting its work or something like that. So there are some strategies that can be used inside a program to deal with these things, but they can be pretty insidious. Okay? Any questions about the notion of deadlocks? All you really need to know from this course is to understand the concept and understand the gridlock analogy, and you'll see the concept and realize that in systems, multi-threaded systems, it can be a real threat at times. And Java, by the way, is prone to deadlocks internally when you're programming. Anytime you use the word synchronized, what you're doing is you're locking objects. You say synchronized, you execute that method. Until you exit that method, you're locking the object that object is running. That method is running on. Okay, and therefore any other thread that tries to access the same object for writing will end up being hung, waiting for you to finish. Okay. So you can end up with exactly this situation. The second major classical style of timing defects are called critical races. Okay? So in general, a race condition is a condition where you have some calculations going and going and going and going, and it ends at some point. Okay? So imagine a race. A thread starts executing and ends up finishing at some point in time. another thread started at the same point in time, executes and executes and executes, and depending on the calculations it does on that particular run, it may end up winning the race. It may get there first or may get there behind the first thread. Okay, so that's fine. Okay, two threads end up ending at different times. Not a big deal. The problem is when this race can become what's called critical, when it really matters which one ends first. And it's critical that the first one finish the race first, because otherwise you get bad results. You get invalid calculations being done. So that's the notion of critical race. And a critical race can occur and can give rise to bugs when you design the program with the expectation that that first thread will always finish first, but doesn't sometimes. And the doesn't sometimes is the bug. Okay, or the failure in this case. The defect is the expectation that one thread will win, and the failure is when it doesn't and some invalid calculation results. Okay, so how do you test for this? Well, you test for this again by doing things, by playing with the program, by trying deliberately to slow down threads and speed up other threads. Slowing down threads could be done, for example, by giving them larger volumes of input than they would normally expect. Trying to force them to do bigger calculations, just to see what would happen. You might end up getting a deadlock, you might end up getting a critical race and invalid results coming out. So see if you can overload the system in strange kind of ways. But inspection is still a better way of detecting these things. Okay, so here's an example of where a critical race could cause bad results. Imagine that the normal circumstance is I have thread A that executes, finishes, and sets a data value. Thread B executes and normally takes a longer time and eventually gets down to the point where it will get that data that was set by thread A. Fine. So the data is set, and then B gets the data and does its final calculations. That's the way the programmer designed it. So now what happens if all of a sudden thread A is held up? Maybe some maintenance work goes on, somebody changes the program and adds extra computations to thread A, so thread A slows down. Or what if thread B is put on a faster CPU all of a sudden? They're running on different CPUs, thread B is put on a faster one, upgrade the hardware. Wonderful, good idea. Wrong. Okay, because now thread B gets its work done first and gets around to the point where it gets the data. But the data hasn't yet been made ready by the other thread. And so now what we have is we have thread B getting invalid data that's garbage or from a previous run, assuming it's valid and doing its work, giving incorrect results of some kind. Okay, and then finally, thread A finishes its work, sets the value, and that value is never used because the consumer of that data has already done its work incorrectly. Okay, so this is a classical situation of a critical race where now thread A is losing the race, thread B is winning when you expected it to be the other way around. Okay? Now there are strategies when you learn how to do real-time programming, and there is a course in real-time programming in the computer engineering program, and software engineers will learn some of these issues in their telecom and other software courses. You'll learn about strategies for designing real-time systems to prevent these kinds of circumstances. Okay, any questions? Right now, I'm teaching it in the context of testing because it's testing where you have to typically first become conscious of these things. You know, you'll often end up testing a wide variety of software and detecting these kinds of problems well before you end up getting deep into the design issues. But sometimes you might end up designing these types of systems first before you start testing. There are strategies that prevent critical races, and these strategies often use locking mechanisms. Okay, so I will, in the previous slide, I will avoid accidentally getting a value before I set it by having thread A lock the value, lock the data, and so that if thread B by happenstance gets to try and access the data, it finds it's locked and waits until thread A unlocks the data. Okay, that's a strategy that you can use to prevent critical races. The problem is that this can give rise to what? If I start locking things, it can give rise to deadlocks. Okay, so sometimes the cure for a critical race gives you a deadlock situation instead. So you have to be careful in the use of these things. And here's a more sophisticated example of the use of synchronization to try and deal with some of these circumstances. Now I have, on the left-hand side, I have thread A getting data, doing a calculation, putting a result. I have thread B getting data, doing a calculation, putting a result. But the problem here is that the put of A is immediately followed by a put of B, and so the A's calculations are wasted, or there's certainly something erroneous here, because B is just overriding A's put immediately, and therefore A might as well not have done its work. And so what's presumably intended is that one does its calculations first, and then the other one comes in. So on the right-hand side, I've got A getting the data, calculating and putting, and all that while it has a lock on the data, and so then only when the lock is released can B get the value, do its calculation, and put the value. Okay, and that is more reasonable. Certainly what we see on the left is a bit strange, where you have two puts following each other. Okay. There are, in fact, debugging tools that will exactly help you find this situation. If I ever have a situation where I set a variable, and then I set the variable again, without any intervening read of that data, that's a sign that likely there's a bug in the system. And so there are debugging systems that will help you find those. You can analyze them and see if, in fact, that's a problem. And you can use those in testing, in white box testing, to go in and see if you can detect these double writes in a sequence. Any questions? Okay. So we'll leave the timing and coordination defects and move on to another category. Stress and unusual situation defects. Okay, these are defects that are found, that should be tested for in pretty well all systems. Okay, the first one is insufficient response time or throughput. Okay, the system's running too slowly. And we have to test for that. This is something which we have to test for. The requirements should specify a response time or a set of response times for different transactions, and we have to see if we can get the system to exceed those response times. Remember, our job is to see if we can break the system. So we try and find circumstances, large volumes of data or whatever, where these response times are not being adhered to. Okay? Now, if your job is to try and break the system, first thing you're going to do is you're going to run it on the slowest system that your users might legitimately use. Okay, so you have to find out what that is. Okay, the sort of standard thing we think about in industry is to say that users are likely to be using computers that are up to about 3 years old. Okay, it's legitimate to say that a computer that's more than 3 years old, maybe the user should be asked to upgrade, certainly upgrade the memory, if not upgrade the hardware. But that does depend on the company. I mean, there are certain circumstances where people have specialized computers or very specialized hardware where the hardware could be much, much older than 3 years. And they can't replace it because it's very specialized. It's not just ordinary run-of-the-mill PCs. It's something more special. Okay? And so you have to understand what is the age range that your users are likely to be using. Find out what that minimum configuration is, and then try and test to make sure that the throughput and or response time is correct and met on those slow machines. Okay? And so what you just do is you do testing with a large amount of data, or a large number of tests, or load the system up with whatever other programs are supposed to be running, get them running full blast, and then double check to make sure response time is still adequate. Okay? This is a typical style of test. A lot of these stress and unusual situations tests are things which are often omitted by testers, but they can be very important. Okay. These days we have to think about network transmission as well. So if you're testing a website, you've got to test this website in a variety of circumstances. The classic thing to do is you test it in-house. You get the website up, You bring up your web browser and you start testing. Well, you've got a local area network connecting to the damn website, so that's not a problem, right? You're going to see this brilliant response time. Okay, so you think, well, I'm going to be a bit smarter than that. I'll go home and connect to my Rogers cable modem and see if it's good there. And it seems to be fine, so that's great. Well, what if your website is targeted to the general population? Well, I better go and get on a modem. And so I get on a modem, 56K modem that's running at, say, 30K or something, and test it there. Certainly you should do that if you're designing a website that's designed to be used by the whole population, because, you know, considerable percentage of people in Western countries have high speed, but, you know, there are still plenty of people in rural areas who cannot get it, and there are plenty of people who don't have it for one reason or another. And if you're designing a system that's supposed to be used worldwide, the larger market share in the world and the fastest growing market is in ordinary modems. Okay, it's growing much faster than high speed because of third world countries, you know, coming online, and they don't have high speed at all. Okay? But that's not enough. Here's another situation. One thing you've got to realize is that if you have an ISP that is on one part of the internet, and you are expecting users to use it from all over the internet on different ISPs, some ISPs have very lousy connections between them that have a lot of routers connecting, and there's a lot of latency and a lot of delays from particular sites to other particular sites. So you need to go and you need to log on to people who have connections to a wide variety of ISPs in a wide variety of places to make sure that in actual fact your application is performing adequately. There's a number of quite well-known websites that I've run into that will not work properly on a local high-speed connection, merely because they have too much latency, too much delay in connecting to some other ISP somewhere else where the website is. And these other websites sometimes give up. There are certain styles of web servers that give up quickly after detecting a certain amount of delay, and give very, very, very poor throughput. Okay, so lots of subtleties in testing for response time, especially when there's network involved. And there's a number of very well-known systems that are very bad in that respect. Incompatibility with specific configurations of hardware or software. Okay? Oh, this is the real bane of a lot of systems. Okay, so you design your system, you've got a nice, in your company, you've got a nice setup where everybody has got the same Windows machine from Dell with the same sound card and the same version of the operating system, and you develop for that, and then you fine-tune it, and it's working just beautifully. And then you go stick it out, and somebody else has got Windows 98 or Windows 2000 or the next version of Windows that you didn't have yet, and a different sound card, and a different kind of network, and other kinds of things that are subtly different, and the system crashes and doesn't work. Or they've got some other kind of software installed that is using a similar dynamic link library but not the same version, you know. All kinds of weird things. Everybody knows this is the nightmare of computing in today's world. So you've got to test on all kinds of strange configurations. You've got to go and test this thing in customers' environments. If you have one customer, that's a bit easier. If you have multiple customers, then you have to try and find a wide variety of people who have different kinds of configurations of hardware, of operating systems, of other software, strange configurations, strange pieces of hardware plugged into their systems, different kinds of networks with different settings, and still make sure your system works. Okay? And until you've done a large amount of that, you can't be confident that your system is ready for the open market. Okay? And how do you know what to test on? Well, it requires skill. It requires an understanding of the subtleties. If you're just writing a very, very dead simple program that is not doing much in the way of networking or using of hardware, you're probably safe. But if you're doing a program which is doing anything unusual, then you have to start worrying about these configuration problems, especially if you're using dynamic link libraries or other kind of system extensions or special hardware. So, second category of stress in unusual situations. The third one is related to the first. The first one we talked about was throughput and response time. Okay? The next one is handling peak loads. Okay? Or missing resources. The peak load notion is the notion of I have other programs running or other network access going on, and at times that will mean that there's not enough memory available or not enough network available for my application. Okay? And so what you have to do is you have to try and simulate, when you're testing, these peak situations where resources are being used excessively and see if your program can survive. Now, it's not a question of necessarily giving you the response time you want. What you want is to survive through these peak periods where you understand that sometimes you can't get response because there just aren't the resources there. But you still shouldn't have crashes, or you still shouldn't have invalid data being saved, or other kind of strange results. The system should maybe slow down gracefully. Maybe it should display messages saying, please try again later, network problems, or something that the user will understand, you know, and will realize that they can perhaps wait, come back later on. And so we have a number of things that could be in short supply. Memory is one, because lots of other applications running. Could be disk space. Okay, this is something that could happen either sporadically because of some process that uses a lot of temp space, or it could be something that creeps up and hits you all of a sudden and stays there until somebody cleans up. It could be network bandwidth, which is typically transient. It could be caused by malicious programs. We've had a number of those kind of things here. Hackers really love to hit universities. Probably some of the people doing the hacking are in the universities, but anyway. And so sometimes network bandwidth grinds to a dead halt, and you wonder what's going on. And then another situation is permission problems, okay, where you have read-only or inaccessible files or other resources because somebody's done some inappropriate configuration. So the key is that the program should be tested. The program being tested should report the problem intelligently and not just crash in some unexpected way. So when you're designing programs, you need to design for these situations, and when you're testing, you need to simulate them to see if the program in fact does handle them intelligently, and does give a result that you would expect. And a lot of problems in systems are caused by these kinds of defects. Okay. So to devise a method of denying resources, you just create a massive file that takes up almost all your disk space and see if the system, you know, at least gives an intelligent message, or eat up the memory, or run it on a machine which has too little memory, things like that. Okay. Any questions about these unusual situations? We say unusual, but the point is that over time, the unusual becomes the usual. Right? Given enough time, all of these things are going to happen. And so they may be unusual on a particular given day, but at some point, these things are going to happen. And when they happen, they can be quite annoying to users. And so you want to try and make sure that they don't occur. Inappropriate management of resources, closely allied. In the previous case, we were talking about resources being used up by other programs, running out of disk space because another program ate up the disk space or the memory or the network bandwidth. This is a situation which is your program that is inappropriately using resources. So what you need to do when you're testing is you need to make sure that your program, for example, does not have, and the classic one is a memory leak. Memory leak is where gradually over time, it executes over a long period of time, gradually builds up the amount of memory it's using and doesn't free. Okay, now in C and C++, that is a classic problem. In fact, a significant percentage of all C and C++ programs are prone to memory leaks. And they're very insidious, and there are packages you can buy that will, specifically, their job is 100% to detect memory leaks. They will monitor your use of memory and give you reports as to how much memory you're using, because you forget to free memory or whatever. Even in Java, however, it is possible to have memory leaks. It may surprise you because you think, well, we have garbage collection. But what can happen is that the garbage collector only kicks in, okay, if there is no reference to an object, and that object cannot be used again. But what if you put an object in an array or something, or in a collection, and you keep adding objects to this collection and forget to take them off the collection? Well, the garbage collector is going to say, well, that's a perfectly valid object. It's in this collection. We know about this collection. We're using elements in this connection. We just might not be using some of the ones that are theoretically garbage. Okay, and so you keep adding things to this collection, this vector or this array list or something. Keep adding, keep adding, keep adding, and you have effectively a memory leak. Okay, so your job when testing then is to see if you can simulate situations which will give rise to memory leaks, and you just simply execute the system for a long period of time doing a lot of work, and take a look at the amount of memory it's using by using monitoring tools that are available that will tell you how much memory each process is using. That's all you do. Relatively straightforward, but it takes time because you've got to run the system over a long period of time to see what's happening and doing all kinds of different transactions. You know, executing it extensively with all the possible things, because the memory leak may only occur in certain circumstances. It's a bit like trying to test for deadlocks. You know, deadlocks only occur occasionally. Memory leaks, they're usually more common in the sense that if there's a memory leak there, it's probably going to appear more often than the deadlock will appear. But nevertheless, it might only be a very gradual increase in memory use very occasionally, and so you have to run the system for a long time. But there are other situations of inappropriate resource management. It could be locking external files or database records and not releasing those locks. Okay, I've seen this happen on a number of occasions where a program has locked files and keeps locking files. There were old versions of Microsoft Word that used to do that on the Macintosh, would lock files and keep locking them forever. You had to quit Word in order to release all these old files that are still locked. Okay, so that's another related kind of a problem. And of course, inappropriate use of too much network bandwidth. Okay, you know, is the program sending way too much stuff through the network, then would be justified. And you can monitor network use to detect that. And then we have recovering from a crash. Heaven forbid we hope crashes don't happen. It's probably a failure if a crash happens. But not always. Sometimes people deliberately kill programs for one reason or another. Maybe the power went out. Hey, the program crashes if the power goes out. So if the system's in the middle of executing and then is cancelled for whatever reason, whether it be a crash caused by the program having a failure or some other kind of situation, power failure, it's still a circumstance where you don't want to get corruption of your data. You want to be able to immediately start the program up again once the power is restored and have everything intact, your files intact, okay? And any other kind of data structures, databases, and so on. You don't want to leave them in an unstable state. And if they are in an unstable state, your startup process should detect that and make corrections, okay? Maybe back out things that were half done. Very important that happens. So what you do to test for this is you crash your program deliberately. You can turn the power off if you want, although that tends to cause problems with operating systems. So you find other ways. You use the task manager to kill programs. You kill them, and then you start it up again and run it and do some stuff. And then while it's doing something, while it's writing a file or accessing a database, you kill it. And then you start it up again. And you do this several times. And you analyze the resulting data and the resulting activity to make sure that in actual fact there's no corruption in the data and it's actually still behaving correctly. Okay, so that's an important thing that for some styles of applications, now not all applications you need to worry about this, but any application that is writing to a database, you do need to worry about it. Any application that is writing files that are then going to be read and processed subsequently, you do have to worry about it. You have to worry about things that are half done. Okay, there has to be intelligent design that will detect that half-doneness and somehow deal with it. Okay, at the very least, it should somehow prompt the user to go back to a backup version or something like that. There has to be some intelligent way of dealing with things because there will always be crashes of programs. As I said, even if it's not caused by a failure of the program itself. Okay, so that brings us to the end of this category, the unusual circumstances. We'll move now on to the final category, which is documentation defects. This is defects where you're giving the wrong information to people. Classically, it was on paper. Now it's most likely to be online help. Okay, it's still a defect, still considered a failure when the user goes and tries to find information and get the wrong information. Okay, so you have to test. As part of your testing regime, you have to test and make sure that the documentation that is provided with the application is in fact up to date, corresponds to the application, gives the right information to the end user when they want it. Okay? So what do? You go through the use cases, making sure that the test documentation corresponds correctly to those use cases. Questions? This is obviously something that is often not done. Okay? People think classic testing. Test the inputs, make sure they provide the right outputs, we're done. Okay? But all of these unusual tests and all of the documentation tests are things which people often forget about, but they can be very important. Okay, so we've talked about the categories of things you need to test for, and the fundamental underlying notion of trying to figure out where these algorithmic defects are likely to lie. In some sense, it's guesswork, but it's more than guesswork. It's very intelligent guesswork. You cannot find all of the defects in testing because there is fundamentally this notion of guesswork if you're doing black box testing. If you're doing white box testing, you can be exhaustive in a much more reasonable sense. But with black box testing, there's a lot of intelligent guesswork involved. The key is to be systematic and to be knowledgeable. And part of the being systematic is to write down your test cases in advance. Rather than just sort of walking up to the system and saying, today I'm going to test, and trying stuff out. You make a list of things you're going to test. It's just like instead of going to the grocery store and saying, okay, well, I'm going to buy a bunch of stuff randomly walking around, you're going to write a list in advance. Okay? Many people do that. And if you don't do that, you sometimes forget stuff. Okay? So that's the concept here. You want to make sure that you don't forget things to test. So you write them down in the list. And the items on the list are called test cases. Okay? And the execution of a test case is then a test. And you very often end up executing a test case several times. One time, the first time through, and then after some bugs are fixed, you test again. So you're executing the same test case another time and another time as different bugs are fixed, and you want to make sure that thing still runs. A test plan is a document, these days as often as not online, that contains a set of test cases and associated other instructions as to how you think testing should be done. Okay? So, it will, it's intrinsically part of what you must do when you're doing project planning, and if you don't do it, you're going to end up with quality, with a level of quality that is less than what would be desirable. Okay? The ideal thing to do is to start developing your test plan very early on. In fact, some people even recommend starting the test plan more or less in parallel with the requirements. Okay? Because once you've got a requirement written down, you can write down a few things to test. And then we talked about this notion of test-first programming, where you in fact write your test cases and then design code that will actually fulfill what those test cases say. That's a style that is becoming popular in some circles today. But the key is you don't write your tests after the system is delivered to you as a tester just before you start testing. You start them earlier on. So in most organizations, design and testing is done in parallel. Design and test case writing is done in parallel at least. And in fact, there's good interaction. You're designing a test case, you detect bugs in the requirements. You pass them off to the designers and say, okay, let's get together and fix the requirements. And the designers find bugs in the requirements and they tell the testers. So there's two people working off the same requirements document, helping each other find defects in it. So here is then one of my styles, one of my lists of things that you should find in any, in this case, a test case document. Okay? And these are the things that you want to record as in each of these list items, each of these shopping list items. The first one is the name of the thing, some kind of identification. So what is it we're going to be testing that the tester can recognize? Typically you give it a number and you give it a few words to remind you what the test represents. Okay? You also need to somehow indicate what module is being tested in there as well. You have a sequence of instructions that say, do this, do this, do this. So enter this value, click on this, and press this button. Okay? And then the expected result, what the system should display, or what the numeric value of the output should be. And finally, occasionally you need to say, okay, once you've done this testing, you've got the system into a strange situation, clean up, and reinitialize so that the system is back to its original state. One of the things that you need to do for each test case is to designate how important it is. Generally speaking, when you're testing, what you do first is you run your most important test cases. The test cases that test the high-level function. Can you log on to the system? Can you enter the very basic information? Can you log off? Okay? And then you have another level of test cases that are testing some things in detail. Testing the detail values of inputs, doing your equivalence class and boundary testing of each input. So that's the level 2 test cases. And then you might have some level 3 test cases that are testing for things which are cosmetic, less important, somewhat more trivial things that we can put the system into production if these things failed, but if there's too many of them, the user would think the system's a little bit clumsy and a little bit weak and not as high quality. Okay? So we normally have these 3 levels of test cases, and you have to figure out what level each one should be in. Okay. So usually a few level 1s, a lot of level 2s, and a varying number of level 3s. Other organizations will use different styles of numbering. Sometimes just 2 levels, sometimes 4. But you need to prioritize, because you can't choose what work you'll do. If I went to the grocery store and I only had 5 minutes to shop, I would have in my mind, okay, well, I desperately need eggs, milk, and bread. I can survive without, the strange things, the caviar and the strawberries and the ice cream, But I really do need the bread and the milk and the cereal, So they're the level 1s, and the level 2s are the other things that if you had more time, you deal with them. There's a strategy for figuring out what to test that basically says systematically work through the requirements, circling things that need to be tested, and then turn them into a list. And this is called enumerating the attributes of software. Okay, so an attribute of software, and this is not used in the same sense as UML attributes in your class diagram. Okay, this is another notion of the word attribute. It's a testable thing, testable attribute, something which needs to be tested. And so you systematically circle these things in the requirements, and then you make sure that as you write a list of test cases that each of these attributes is tested. Quite often, a testable thing will require many tests. So for example, if in the requirements it says that a certain field has a month number from 1 to 12, that's going to give rise to a bunch of test cases. Okay? And once you've written those test cases, then you can check off that attribute and say, we've done that one. But it's just a way of being systematic and a way of making sure that you've covered the entire requirements document as you make your list of things to test. Okay, now once you've got your list, how are you going to do it? Okay, so if I have a large number of things to buy at the grocery store and the hardware store and the automotive store and a whole bunch of other stores, am I going to go out one day and say, I'm going to buy all these things today? Okay, and then load them all into my vehicle and get back home and make sure everything's okay? Or am I going to make sure I haven't run out of money in my bank account? Or am I going to do it a bit at a time and say, okay, first of all, I'm going to do the grocery shopping and get that done and get that cleaned up. Then I'm going to go and do the hardware shopping and get that done and cleaned up. You probably would break things up into groups and do them bit by bit. Okay? And so Big Bang testing is the notion of doing it all at once. And what we instead prefer to do is do testing incrementally. The analogy with shopping doesn't quite work, because incrementally usually means that you're going, rather than doing strictly partitioning into sections, you're doing it in levels. Okay? So you're going to be testing maybe the database layer. And this is why this is getting back to the layered architecture, why layers work so well. They're testable. You test the database layer. You test your network access layer. Maybe you test your user interface with a dummy system underneath it to make sure the UI works. And vice versa. You test the system without the UI by plugging values into the API directly. And then you plug it all together. Okay? So this is called incremental testing, where instead of testing the entire system at once, you test pieces of it. And gradually putting the whole thing together. And it can be done horizontally or vertically. Horizontally means you're testing different subsystems. Vertically means you're testing layers and adding, as you add layers on, either top-down, bottom-up, or in the middle, towards the middle. Okay. The key is that Big Bang testing the entire system all at once, tends to miss things because you're just testing a system which has got so much stuff inside it. If you tested just particular pieces, you're going to find bugs rapidly in networking or rapidly in database that would only very occasionally show up with input that comes in through the user interface, but will show up immediately if you're testing each individual subsystem. And also, if I'm doing Big Bang testing and I get the wrong result, hey, what is it that caused that bad result? Is it a database problem? Is it a network communication problem? Is it a problem in my computations in my functional layer? Or is it the user interface displaying it wrong? I don't know. Okay? And so it's a lot of more work to dig up the bug. So incremental testing is the style that's preferred. And integration testing is incremental testing where you gradually integrate more and more stuff until you've finally got the whole system. So as with design, we can do it top-down and bottom-up. Top-down, it says we're going to start by working with the user interface. Get the user interface working with dummy stuff below. Then we're going to add the functional layer with dummy database and dummy network. And then we're going to add the networking in and make it fully networked and with a real live database. Okay? So that's one strategy, and it parallels top-down design. The other strategy is bottom-up, where we say we're going to test at the lowest level layers and then add a layer and test and add a layer, and finally we add the user interface on top. Okay? So we can do that too. Sandwich testing is typically what most people do, just like you do a bit of top-down design, a bit of bottom-up design. You're going to do a bit of top-down testing, a bit of bottom-up testing. It's convenient to test bottom-up in many ways because you can easily test a database. You can easily test a network layer as long as it's got a well-defined API. And you can easily test a user interface by putting on some dummy underlying system that generates random data. Okay, those things are easy to test, and once you've got those out of the way, then putting the middle piece in and testing it is also somewhat easier than Big Bang testing. Okay, we've got this notion of stubs and drivers in testing. You need to know the terminology. A stub is a piece of code that is providing lower level functionality in a dummy way. So it's providing dummy data for your higher level layers to use. Okay? A driver is the other way around in testing. A driver is where you have a dummy higher level layer that is driving the lower level layer. Okay, so I put a dummy UI on, or I put a dummy layer in that's going to be poking my API and doing all kinds of calls to it. It's not really the UI, but it's some other just pure test program. In the book and on the website, there is an example of a test driver that test drives the OCSF system, okay, and sends messages backwards and forwards. And it's quite cool actually. It works. Try running it. It works live. It's got a nice user interface on top of it, and you get flashing lights going on and off. As different clients get into different states, they go yellow and red and green and things like that. So it's kind of Robert Lagunière, my co-author, wrote it, and it's really one of the coolest things of the book. So try that out. But it's a test driver, and it really does a good job of testing. We really used it, and we really detect bugs in the OCSF using it. So, and it's still there, and we now will use it for what's called regression testing that we'll get to later on. If we make any changes, we just plug the same test driver in and make sure that those changes haven't broken the system. Question?
Do you test code coverage?
Okay, his question was code coverage. The notion of code coverage, I think, is something that I'm not talking about in these slides. The notion of code coverage is testing to make sure that every branch is executed, or alternatively, every statement is executed, or alternatively, that every condition, that all the possible conditions are reached. Different notions of code coverage. And it's normally something which is talked about more extensively when you talk about white box testing. Okay, because with black box testing, you can't see naturally what the code is there to cover. Okay, you can only make some guesses, but you can't accurately measure code coverage unless you have a tool underneath you that's just giving you some percentages. Even then, you're starting to move into white box testing. So code coverage is a style of white box testing that where you actually verify that you actually executed every statement in your program, or some high percentage of them, or some high percentage of branches. Okay? Yeah, it's in the book, but it's something that I'm not going to go into in these lectures right now. Any other questions? Okay, so we have a number of strategies for testing illustrated graphically on slide 52. Top-down testing. Start with my UI layer with some stubs. Add on a functional layer with some further stubs that are testing the even lower level stuff. And finally, I put everything together with all my layers. Bottom-up testing. Start with some drivers on my database and network. Add some more drivers simulated in the UI, and then put it all together. Sandwich testing. Several different strategies, but one might be test the UI layer with some stubs, test my database and network with my drivers, and then put it all together. Okay? So that kind of sums up those concepts. So now, what happens if a failure occurs? Okay, what if things go wrong? Well, we have to have some systematic way of managing these failures. We have to have a failure tracking system, often called a problem tracking system, problem reporting system. This needs to be set up for our testers to use, and typically will then also be used by end users to report problems as well in many circumstances. And you need to have a change management protocol where you screen each reported problem, give it a priority. You know, how bad of a problem is this? Somewhat based on the level of failure, but also it could be the frequency with which this failure will typically occur and the devastation it causes, if any. Okay? And you fix some of the failures, others you can't. So you fix some of the defects, others you can't because you don't have time. So you put them on a release notes when you release the software. I'm sure you've all seen that. Install software and it says known bugs. Okay? And some failures some defects you do try and fix, and you end up then creating a new version, and that has to be tested again. So you have this test, fix, test cycle. As each time you fix problems, you have to test again. And unfortunately, what happens is as you fix problems, that gives rise to new problems. And so we have what's called the ripple effect. And the ripple effect is where you continue to have new problems occurring because the old ones were fixed incorrectly. And we talked about that concept earlier on. And the system is sometimes said to regress into a more and more failure-prone state as you fix bugs incorrectly. Especially if you're rushing to meet a deadline, you fix bugs, add more bugs, and the system gets into a worse and worse state over time. And so what we want to try and do is we want to do a thing called regression testing, which is making sure that the system is not regressing into bad states by introducing new bugs as we fix old bugs, okay? And to do regression testing effectively, you avoid testing every single test over and over again, every single test case. You pick a subset of these, an intelligent subset that you think would give you a good selection, a good coverage of the system as a whole, but it's usually too expensive to do regression testing on all of the entire test plan. Okay, so regression testing is testing usually on a selected subset. One thing to remember is this thing called the law of conservation of bugs. This has been found to be remarkably true. It's not a law of physics, but it's something which has been observed over and over again in software systems. If I have a buggy system, then the number of bugs remaining is proportional to the number of bugs already fixed. So if I have a large number of bugs, that probably means there's a large number of bugs that will have to be fixed in the future. If I have a high-quality system where I've rarely detected bugs, that probably means there's relatively few bugs left. This may seem totally counterintuitive. You might think, well, as I'm fixing bugs, I'm going to be getting a higher and higher quality system. The problem is because of the ripple effect, typically we will have new bugs, but also, if the system was bad enough to start with, that I had bugs to start with, it was probably badly designed, And so probably that will make the ripple effect even worse. A badly designed system that gave rise to large numbers of bugs will be harder to fix and will probably cause you to have more bugs in the future as you fix new bugs and as you make enhancements or try to make enhancements. Okay? So the law of conservation of bugs, we try and combat it by effective regression testing, but we also have to realize that if we've got a really lousy system that we may have to redesign it or redesign parts of it. Okay? Okay, the final thing I want to talk about today, just very quickly, I know we're almost out of time, is when do you stop testing? Okay? You don't stop testing when the worst thing to do is to say, okay, we'll test for 10 days and stop, because then you might not have finished your test plan. Okay? And an equally bad thing to do is to say, we're going to stop testing when we have got to a point where we haven't we think we don't have any more bugs or whatever. Okay. The basic rule is that you have to stop testing at a reasonable point. You can't exhaustively test forever, and you shouldn't stop testing prematurely. And what they suggest is that you, first of all your level 1 test cases pass. Secondly, you've got predefined high percentages of level 2 and lower percentages of level 3 test cases all pass. So say 95% of your level 2s and 75% of your level 3s. And that it seems that the system has been stable for a while. As you keep testing it for a few releases, it's reasonably stable, okay? And at that point, you might legitimately say we can stop testing. You're not going to test too much, and you're not going to test too little. Okay? So we've basically got to the end of the testing section. Next lecture, we'll talk about inspections briefly, and then survey the final chapter, chapter 11, and that will bring us to the end of the course.